Okay, now we're into the last section, last bit for topic 2. Same as the gas absorption case, a typical cooling tower is represented like that, where we give you the water flow rate and the air flow rate. Does it mean that my column can only operate at this condition? So for this case, what is determined by the plant side from the operations? It's actually how much water that is coming back to this unit. Okay, sometimes they produce more and sometimes they produce less. Sometimes the temperature comes in higher, sometimes the temperature comes in lower. But remember, for this particular cooling tower unit, you cannot tell them to change because their process needs it. They will send to you whatever they have to. So for you, if you are in charge of this unit, alright, the only thing we can manage is the air side. Okay, and in real, the only thing we can change is the air flow rate because we can't really change the air humidity. That one is fixed by our environment. Okay, so the only action that we can actually do is the air flow rate. So that's exactly it. If I want, we need a compressor or blower to be able to push this air through your column. So if the flow rate is high, well, my equipment will need to use more electricity or energy. Okay, if my flow rate is low, then it will use less. So for this case, we want to think about, can I reduce this and what's the furthest I can reduce it to? So this is the G minimum, the minimum G value I need to have. So the concept is the same as the gas absorption one. Okay, a normal operating line that we have drawn so far looks like that with the curve. Now operating line looks like that. Okay, the slope of the line is given by LCL. We had derived this in our earlier equations. So now we're saying that in a particular process, I would like to reduce my G, my airflow rate. I would like to reduce my airflow rate. So what's the implication if I reduce my airflow rate on the operating line? My slope, my gradient will, if this is lower, my gradient will go up. Gradient go up means that your line will shift in this direction here. And so it can shift, and what's the furthest it can shift? And this is the part that you need to locate. You still need to cool from TL2 to TL1. The furthest you can shift is, my graph is bad, but never mind. TL2 is here from the graph. The furthest you can shift is when it hits the equilibrium curve. That means your line will go higher and higher and higher, and the furthest it can go is when it touches. Can you see how we draw this line compared to this line? Same, huh? Okay, so the way to solve this is the same as the previous. We're just going to equate the gradient. This particular gradient now, this new gradient is now LCL over G minimum because we are reducing the G until the minimum value. Alright, so essentially to solve this is that, considering from the previous case, gradient LCL over G minimum. How do you find the gradient? Well, literally from your graph. So let's look on my next page. Have I given you the graph? Yep. This was what was plotted previously. Okay, so we need to draw our G minimum line. So at 43.3, I need to draw up until it reaches the G minimum, the equilibrium curve. Okay, so I will try to draw the minimum line. Okay, one thing you notice, if I were to attempt to draw it this way, it's going to cut the equilibrium curve. Okay, so please take note, operating lines can never cut equilibrium curve. So what we do, we will hold this point, this initial point, and we just bring it down until it just tangents it. That's the furthest it can go. tangent. Okay, where it should touch. Okay, and that would be your value. Alright, so draw your minimum line. It should never cross, cannot reach there, so you have to come down and tangent it. Okay, so we just need to find the gradient of this line, delta y over delta x. So looking at this one is about 0.190. So 190,000 minus your initial value is 72 over your delta x, which is your 43, your TL1 28. Okay, this is the gradient of the line. Literally we read from the graph, delta y over delta x equals to L, which is your same L as before, 1.356. CL is 4187, which is given, and this is your G minimum. So you look at this, one equation, one unknown, you can calculate G minimum 0.742 kg dry air. That's how you find G minimum. And in real, do we ever operate at G minimum condition? Of course not, right? Because technically no column can ever reach equilibrium. So we would again operate at about 1.5 times the normal here on top. 1.3 to 1.5 times G minimum. Okay, and that concludes the lectures for topic 2. Thank you.